Okay, so indeed I will talk about exclusive vector meson production at next reading order in the Color Glass Condensate framework. So let's start with the basics. So what is meant by exclusive vector meson production? So the way we usually think of it in theory is that we have some photon, which can be virtual, and then it interacts with some target nucleus, and in the end we have only this single vector meson produced. So it can be like a light vector meson, so rho phi, or heavier ones, so j psi or upsilon, for example. And why these vector mesons that we are usually looking at is because they have the same quantum numbers as the photon, so they are kind of like easiest to produce. Also, there's no color exchange, or like the photon and the vector meson are color singlets here, so this is a diffractive process. And also we can classify this in terms of the meson polarizations, so longitudinal transfer polarizations, and usually we take the meson polarization to be the same as the photons because this polarization mixing is quite suppressed. And this kind of process can be measured in DIS, where we have an electron emitting the photon, or also in UPCs, in ultra-peripheral collisions, where one of the nuclei emits a quasi-ray photon. So why this process is interesting is because if you go into high energy, you find out that this cross-section goes like the gluonicity square. So it is very sensitive to the gluon structure of the target. And also because it's an exclusive process, we can actually measure that momentum transfer between the photon and the target. And by a Fourier transform, it is conjugate to the input parameter. So this gives us information about this spatial distribution of small gluons.
So
yeah.
Please change the order of the 3 gluons. So the gluon to the power 3.
Not for vector mesons. And on the other end, many of us don't think it's been seen yet.
Yeah, so if you would be interested in Oderon, I guess you would need to study like pseudo-scalar production. So see, for example. But the thing is actually, if you go to the very high energies, it becomes suppressed. And it is very hard to measure.
And it's not just the cube of the gluon distribution, it's only valid. Some approximations.
Yeah, some approximations go here about that. Anyway, the point is, it is very sensitive.
This is really exclusive process, right?
Yeah.
So, like the target essentially intact, then you produce.
Yeah, so the target can also dissociate.
But that's not.
But yeah, you have a rapidity gap like in the photons.
Yeah, then if you dissociate, you don't know, but that's really an exclusive process.
Well, it is.
Unless you can count number of nuclei in the dissociation, there are no extra Hadron production.
Well, I think what's important is this rapidity gap between the vector meson and the target.
Okay, yeah, then that's not exclusive process.
Okay. Yeah, so we also allow for target dissociation.
Yeah, that's a diffractive. Right.
Oh, yeah.
But there is two kinds of coherent and incoherent. And if you want to measure the
No, he's talking about his title is exclusive process.
But your focus is on coherent, right?
Yeah, my focus is on coherent.
Okay,
yeah. I have never thought about.
Title is exclusive. Right?
Yeah, I have never thought about the term like that. I have thought that it includes both.
So the target doesn't break.
Yeah, but okay, we will focus on the case where the target doesn't break. Yeah, although I will briefly mention. So yeah, because both are interesting.
But if you're gonna not allow, I mean, there's a continuum. There's soft Bremsstrahlung coming off from everything. I mean, where do you draw the line and say, a 1 EV photon Bremsstrahlung, it's still coherent, 10 EV it's not, or 100 AV, or, if you start allowing things to happen, one is that happens, they're infrared divergence, but where do you draw the line?
I think.
Well, what's the question about?
Well, you have an ion.
They were talking about photon productions.
Well, but there's still the target.
Yeah.
There's Bremsstrahlung photons.
No, he's talking about vector mesons. Right.
No, but you have a vector meson, and you have the reaction he showed on the last slide, plus the Bremsstrahlung photon.
Yeah, that's fine.
There's no photon.
And you're saying that there would be extra photons here.
Well, I'm saying an extra photon coming from the ion. I mean, it's suppressed, but it's still there.
Oh yeah, here.
And so, question is, where do you?
That's still computing.
Oh, you mean UPC case?
Any case.
No, for the proton, you don't worry about it because that's really alpha correction.
Well, alpha, but it's 1/10. I mean, if you're talking about exclusive or not, the photon matters. I mean,
Okay. Unrelated to the photon, I think somebody has their audio on, it's not, I mean, there's a little faint echo. I don't know if the remote people bother us or not, but.
Sorry.
No. Right.
All right, so yeah, so there's some technicalities if you look at incoherent correction, I guess, but usually when people look at this, they divide this into coherent and incoherent correction, where coherent, you kind of, in this picture that we are using, you have to take these different target configurations into account, which is these angle brackets here. So in coherent correction, it is taken at the amplitude level, and here the target basically stays intact, and this probes the average interaction. Whereas in incoherent correction, you have kind of this variance of the amplitude, and here the target dissociates, and this probes the event-by-event fluctuations. But yeah, I will focus only on the coherent correction. And if you look at the dependence on the momentum transfer T, then you can see that for different values of this, the coherent or incoherent is more dominant. But one reason why I'm focusing on the coherent correction is because we want to look at small momentum transfers.
No, here, I mean, you're really talking about whether coherent or incoherent is that whether you see the target is dissociated or not, right?
Yeah.
Yeah, and then, yeah, okay. I still, maybe you could explain later on what is the bracket, what is the other
Yeah, maybe it will become
would that mean
more clear later. Yeah.
you probably explain later, yeah.
Yeah. So anyway, we are considering this in the high energy limit. So it is more convenient to use these light cone coordinates. And also, we usually choose such a frame that this incoming photon has a large plus momentum and a small minus momentum, and no transverse momentum. And then you can choose the target to be rest or whatever. This is actually not literally boost invariant, but it's one approximation one can make. But the point here is that when the photon has small q minus, then you can think, okay, in the plus direction, it has a large wavelength, which is larger than the target size. So from the photon's point of view, this target is an instantaneous shock wave in this light cone time x plus. And this then leads to factorization. So when we are considering this process, you can actually kind of neglect everything that happens in the shock wave. So before the process, the photon has to fluctuate into a quark-antiquark pair, for example, because photon is a color-neutral object, and this is dominated by QCD. So the simplest case is if it's a quark-antiquark pair. And then this quark-antiquark pair interacts with target, and we use the Iconal approximation. And then after the interaction, then this quark-antiquark pair forms your final state. So in our case, the vector meson. So this is the leading order picture of this. So at higher orders, you can also have additional gluons here, for example.
Yeah, of course.
Yeah.
I mean, you will use shock wave. I want to ask, can you estimate the time scale of the dipole nucleon interaction?
Can I estimate?
The time scale, how long it takes for the dipole nucleon interaction? Is it continuously or?
Yeah, so
When you can separate, you can do factorization, different process, project them together.
yes, so usually one thinks that it is suppressed in terms of the energy of the photon target system. So you could say it's a suppression in q squared over the energy where q squared is the photon virtuality, for example. This one way to think about it. So it is basically like the suppression in Bjorken X. So you would think that the terms that don't follow this are suppressed by Bjorken X. Okay, so the way we calculate this then is that we use this so-called light cone perturbation theory. So because this dipole target interaction is instantaneous in this light cone time, it is more natural to use this light cone time as your time coordinate. So usually when you do your standard quantization of your fields, you quantize them at equal times. But in light cone perturbation theory, you use the equal light cone times. And what this basically means that if in your standard perturbation theory, your momentum is conserved and then your energy is not, then in light cone perturbation theory, the transverse momentum and the plus momentum are conserved, but this minus component plays the role of the Hamiltonian. And then when we do it this way, we get slightly different Feynman rules. And also one caveat is that light cone perturbation is time ordered. This has some advantages. One is that all particles are real, but the disadvantage is that you have much more diagrams to calculate. Also, you get some additional Feynman diagrams that you might not be familiar with. So you have these instantaneous interactions, as we call them. So they are kind of 4-point interactions with, for example, like quark going into quark, and there's like an instantaneous gluon exchange.
What does this mean, no particle creation from vacuum?
Well, basically, you cannot have like a diagram of this if that time goes over. So usually, I think if you did this using the equal time quantization, then something like this is possible for brief times. But because we're using different momentum, or because now the T minus is not conserved instead of energy, then the situation changes.
But does it matter for any observable?
Well, the calculations always do some results, but I guess it's if you were doing like this equal time perturbation theory in the time ordered way, you would have something like this. But in light cone time perturbation theory, this doesn't exist. But of course, no one is really using this equal time in the time ordered way, so usually people use this covariant Feynman rules. But in terms of that, for this process, it is quite convenient to use this light cone perturbation theory. And one reason is that if you use light cone perturbation theory, then you can write things in terms of your light cone wave function. So basically, you remember in the initial state, we have this photon going into quark antiquark pair, where this is given by the light cone wave function. And you can just then use this light cone perturbation theory to write your light cone wave function. So if you have some asymptotic state, then you can expand it in terms of these different Fock states interacting with the shock wave, and then you have your light cone wave functions. And the way to calculate this is that we are doing kind of this quantum mechanical perturbation theory, so that you have some matrix elements and energy denominators. So as an example, if we calculate this photon going into quark antiquark pair, the matrix elements or the Feynman rule for this vertex gives you the matrix element, and then you have the energy denominator. And then you can go and calculate this. It looks like this, and we are working in this momenta. So we have transverse momenta, and this Z is the fraction of the particles fraction of this photons plus momentum. And usually we are also interested in this. We want to work in this position space in the transverse plane, so we have to take the Fourier transform of this, and then very generally for photons you get something like that is like a Bessel function. So for photon, one can calculate this quantity, but then we also need this for the meson, which is in the final state. So how does the quark antiquark pair form the vector meson, and that is unfortunately non-perturbative. But in this talk, I will consider two different limits where this meson wave function can be simplified. So for heavy vector mesons, you can use the non-relativistic limit, so you use inner QCD. For light vector mesons, you can then consider the limit where the photon's virtuality is very large, and then basically this corresponds to the leading twist, so you have a leading twist distribution amplitude.
Which barely works. The leading, if you fit like a pi form factor, it never works.
Oh. It seems to work for us.
The form factor for pi form factor?
No, for
Yeah,
vector
for this one, yeah.
distribution
For
amplitude.
pi form factor, never works.
Okay, yeah. So anyway, now we kind of understand this part of the calculation. So these are given by the light cone wave functions. But then we need to still model this interaction with the target. So this is given by something called dipole amplitude. So in the high energy limit, it is convenient to think in terms of this dipole amplitude. So this is a universal object in the sense that it appears in multiple different processes. So for example, in exclusive vector meson production, you have your cross-section being proportional to the dipole amplitude squared. Whereas in inclusive VIS, you can use the optical theorem, and then you find that the cross-section is proportional to the dipole amplitude. And this dipole amplitude can be written in terms of these Wilson lines for this quark and anti-quark crossing the shock wave. So you get one Wilson line for each. And these are really the convenient degrees of freedom in the high energy. So, okay, so that is still something non-perturbative, but it turns out that we can write a perturbative evolution equation for the dipole amplitude in terms of this rapidity variable. So this is related to the inertia of the system. And this is called the Ching-Wall equation, which is very complicated. So usually people take the so-called large NC limit, and then you get the Kolesnikov equation, which looks like this. And then, of course, this evolution is a non-perturbative initial condition. But one way to think about this PK equation, PK evolution, is compared to the D-club evolution. So in D-club, when you go to higher Q-squared values, you're kind of probing smaller and smaller length scales in the target. In the PK evolution, you are basically probing just more gluons there. And it turns out that this gluon density cannot really go on indefinitely. So you get something called saturation in the high energies. So it's basically called the color glass condensate. Now, for the initial condition of the for this PK evolution, what people usually do is that they use the so-called MV model, which looks like this. And then you have some free parameters like this QS squared, which is the saturation scale that you need to fit from data. So usually that is done using the structure functions from Hera. And when you do that, you can get a quite good description of the Hera data. So this is something that is quite well understood. So that's basically the final ingredient we need for this. So let's finally write this invariant amplitude for exclusive vector meson production. So we have just an integral over the photon and meson wave functions times this dipole amplitude. And there's some angle or phase factor like this that depends on the impact parameter and the transverse momentum transfer. Also, maybe I should mention at this point, because I don't think I talked about it before. So when one calculates this, there was this angles in coherent production and incoherent. So one needs to take an average over the target configuration. So when calculating this, one usually models this target as a combination of different classical color fields in the high limit. So the average is just taking this averaging over the different color configurations of the target. And here has already been done, so it's understood that this dipole amplitude has been averaged over the color configurations. Because when you calculate the Wilson lines, it is dependent on the color fields. But anyway, so we have this equation for the leading order, so it's quite simple. For NLO, one gets some additional Raman diagrams, so you can emit a gluon, for example, and then one gets this second line here. And here you also need this photon and meson wave functions for this quark anti-quark gluon state. So this is an additional contribution that appears at this order. Also, this interaction with target is slightly different because now you also have this gluon, but you can write this more complicated dipole in terms of these simpler ones that have like this numbers correspond to the quark and antiquark and coordinates. So you have only 2 coordinates here instead of 3. So it's written in terms of these same dipole amplitudes that appear at this leading order. Also, here we are considering only the t = 0 case because it makes things simple as you can.
So you really need the high Fock state wave function for this calculation.
Yeah, you also need this quark antiquark gluon wave function.
That you can calculate. It's sort of perturbative, right? Gamma into Q bar plus glu.
Yeah.
But the other one is not.
Yeah, that's right. So the way we do this is that for meson, we assume that it first it goes into this quark antiquark pair, and then you have these perturbative corrections on top of that. You have kind of this leading order wave function plus perturbative corrections, and then you have all of these diagrams to calculate. Also, I should mention that because we're using light perturbation theory, these diagrams are different, and also one gets this instantaneous gluon exchange here.
And you could also have, but this is just evolution from the evolution of the lowest Fock state. But you could also have high Fock state. Wave function itself.
Yes. So so let me mention how we calculate the quark antiquark gluon state first. So here we also consider going into quark antiquark state first, and then you have a gluon emission. But in principle, you could have this additional non-perturbative. Yeah. And of course, these are part of the calculation. But it turns out that in the cases that I consider in this talk, so for heavy vector mesons in the non-relativistic limit and the light vector mesons in the high photon virtuality, this is suppressed. So for heavy vector mesons, this is suppressed by the quark velocity. So in NRQCD, you assume that this quark velocity is very small. And for light vector mesons, this is suppressed by the photon virtuality because it's like a higher twist contribution. So that's why we neglect this kind of contribution. And so this is basically how we do it for mesons, but for photons, this is something that you can just calculate. Now, just briefly, okay, this is an analog calculation. We have some regularization scheme that we need to use. So this is maybe a little different than what is usually done in like most collinear factorization calculations. So for the plus direction, we need to actually regulate this gluon's longitudinal momentum. So we use this momentum cutoff alpha, so that normally this Z2, which is the gluon's momentum fraction, it should go to 0, but we cut it off by this alpha. And for transverse directions, we use dimensional regularization. So, but in the end, the alpha goes to 0 and d goes to 4. So, okay, so we then have some divergences. This is how we very generally cancel them. So we have these 2 different parts in the calculation, so quark antiquark and quark antiquark gluon. So if you consider, for example, a diagram like this, where you have some gluon emission before the shock wave and absorption after, this has some UV divergence in the sense that when this gluon has the same transverse coordinate as this quark, then there's a divergence. And it turns out that this kind of combines with this quark antiquark contribution where this gluon loop is before the shock wave. So we combine different terms and we find cancellations of divergences. Then one also needs to take into account the Particle-Kopchak equation. So basically, there's something called the rapidity divergence. So it's you have something that's like a log alpha in your final result, and that is regulated by this evolution. And then finally, we also have this non-perturbative meson wave function for this meson going to quark antiquark pair. And it turns out that this also needs to be regulated, and it's done differently for heavy and light mesons, and I will talk about it shortly.
Jani, a question. So you started with margins at the beginning, or you actually just for this step?
Sorry?
You start with this beam field approximation for the dipole, quadrupole, starting from the beginning, or actually just for the evolution problem? So normally when you do the next linear calculation, what depends on quadrupole? And here you only have dipole, right?
Yeah, but Also without the mean approximation, what it basically does is that instead of having the target average outside here, you can
average repeating.
Yeah.
Okay.
So we could also write this without using it, and then one would use Chim-Wolf instead of PK.
So your for example, your final turn would depend on quadrupole too.
Not quadrupole.
Not quadrupole. So yes, we only have like dipoles, but what matters is how you average them.
That's when you take the non-density or mean field.
So we
So
are.
you mean this process only depends on dipole?
Yes.
That's interesting. Because in principle, generically, your BK depends on not a quadrupole, but two dipole, whatever. You mean?
I mean,
you know what?
yeah, we have this dipole dipole, so
Yeah,
it's
dipole
not,
dipole.
it's not a quadrupole, but
Okay. Okay.
so yeah,
My
that-
bad.
we have this.
Oh, you have that.
Yeah.
So that also appear in the final term.
Yes.
Okay.
Yes. Yeah. Okay, so that was very generally for all vector mesons, but let me now focus on heavy vector meson production. So how do we model this meson wave function? So we use in QCD. So what it basically means that you can do an expansion in terms of the strong coupling constant and the quark velocity v. And the way to do this systematically is to write that, okay, you have this your total wave function in terms of these leading order wave functions, and then you have some corrections from diagrams. And then you can write this in a way that you kind of, instead of having a general wave function for the leading order, you have these different terms where you basically have derivatives of the leading order wave function, and derivatives of the leading order wave function correspond to the relativistic corrections. And yes, so basically this index here tells you about the order of the relativistic correction. So what we do is that we take the fully non-relativistic limits. So then you can say that your leading order wave function is just the delta function in momentum space, so there's no velocity. And in coordinate space, then this would be like a constant function when you take the Fourier transform. So, okay, we write our meson is a combination of quark underquark and quark underquark gluon states. And then it turns out that when you take this non-relativistic limit, you only have these simple forms for the wave function that they only depend on this single constant that is kind of the value of the leading order wave function in the origin. So because we are working in a kind of funny system of coordinates, instead of in just the origin, we also have this integral over the longitudinal momentum fraction. But it turns out that we have the same quantity in both of these wave functions, so that now there's only one unknown constant.
That you always already assume the delta function, right? The phi.
Yeah. So you can kind of say, okay, substitute this wave function, this expansion, then you only have this.
Can you classify?
Yeah.
Maybe this is a parametric approximation. I mean, this I'm assuming that the velocity is in the order of fs. Is that a v is the velocity, right?
Yeah.
So, can you remind me how the argument came out?
Yeah. Why is the
velocity is in order of fs?
I think if you Schrödinger equation, then you could say that, okay, the difference between the energy of the quark underquark state and the meson is like mv squared. Energy or like
in a light hadron ion velocity.
Yeah.
Oh, this
Yeah.
This for the.
Yeah.
I know. I'm asking in R&D why
It's somehow that you assume that like any deviations from the meson's mass is from interactions between the quarks, which are called like alpha s. So on the other hand, you can say it's like
I guess non-relativistic in the first approximation is just delta function.
Yeah, that's the
And
first.
then any like relative motion coming from the radial correction. If that's maybe that's the argument.
So in the
Yeah.
hydrogen atom, which is non-relativistic, like your electron velocity is alpha, right?
Yeah, that's what I'm saying. Okay, thank you.
In naive explanation, basically the derivative always associated with wrong. For example, that have copy there. For example, right? So if you write down current derivative, right, the ground field always associated with the derivative. That have copy in there too. So in a sense, one derivative associated with 1g. So two derivatives associated with Rs.
R here is the dipole size,
Yes.
so why do you set that, just considering R equals 0?
Yes, so you might think that if you were in momentum space, it should be like k is 0, and you would then integrate in current space. This is so. But one way to think about, okay, if you have delta function, okay, think of what is the easiest way to zero this.
So the easy way to understand this, you do the non-relative expansion.
Mm-hmm.
So relative momentum is, you do the expansion, right? So P plus K, P is the total momentum, and K is relative momentum. So you forget about K, but R is basically French transfer conjugate with K. So when you do the K integral, you put R goes there. So it's the dipole size is really related to the relative momentum between these two bars.
Okay.
And then you do the non-relative expansion. So that means your K integral is not limited. So that gives you the function.
So, but if you set k to 0,
Yeah. No, it's not K equals 0. It's K is much smaller than the. So the two QQ bar, the two quark and anti-quark move in the same direction with large movement, or in the rest frame of the component system. So relative transfer relative momentum is very small. So you do that expansion, and then you do French transfer of that restrict yourself R equal 0. Or any correction will be suppressed by one over L quark minus.
Yeah. So also maybe one way to think about this, okay, this wave function is very peaked in momentum, so you can just replace it with the delta function, then take the Fourier transform, and then you find that
R equal 0.
R equals 0. Okay, so we have our wave function. So these factors in front are like Feynman diagonal corrections. So those contain the alpha contributions. And these have been calculated in this paper. Then one thing that we need to do in this to get the final result is we need to renormalize this leading order wave function, so this constant. And the way this is done is that if we were to use just dimensional regularization instead of our regularization scheme, then you shouldn't have this 1 over alpha divergence that appears with us. So one way to see, so we write this our leading order wave function in terms of this dimensional regularized wave function, and then you have this 1 over alpha divergence term, which then cancels with another one into fraction amplitude. But the reason, like one way to see why this works in this way is that you can calculate the decay width of J psi using the non-relativistic limit, and you can calculate using the dimensional regularization, or you can use our regularization scheme, and you find that there's this difference between the two. So this where this relation comes from.
So this one R from the divergence really coming from the one of the gluons attached to the QQ bar in the finite state is soft. Is that right?
So where's this coming from you?
Yeah.
So
I mean, if it's associated with the initial photon side, that may be part of the EK.
yeah, this comes from the meson side.
Yeah, this coming
Yeah,
from
yeah.
meson side.
Yeah, and it's something that you don't see in inclusive DIS, for example. So it's really related to the vectors and wave function. I think it might come from this instantaneous gluon exchange. I'm not sure.
But this cannot be BK, right? Because
No, it's
BK
not.
would be
It's not.
logo alpha.
It's not EK.
Yeah.
It's power.
It's a linear derivative.
Yeah.
So yeah, so it's very funny because usually we have logarithmic divergences.
Yeah, this may relate to, I was mentioning the other days, maybe some of the Coulomb divergence. And some of the NRQCD category also have this Coulomb divergence.
Okay. Anyway, so with all this, you get a result that is finite and be used for numerics. Looks quite ugly. But before I go to the actual numerics, I want to say that in addition to the NLO corrections in the non-relativistic limit, we also include some relativistic corrections at leading order. The reason we do this is that we have found that these relativistic corrections can be very important if the photon virtuality is small. And in terms of NRQCD, these are of the same order as the NLO corrections. So one way to do this is to kind of do a Taylor expansion. Well, in terms of the position coordinates for the Z variable, you have a kind of different delta function expansion, but this is like a distributional identity that you can use. And then you have these constants, which are like derivatives of this linear wave function. Now you don't have any alpha S corrections, so this is a very simple equation. And then you can just use this result, put this into leading order equation, keep terms up to v squared in heavy quark velocity. Then you can also find that these non-perturbative constants can be related to the NRQCD matrix elements. And then you get, for example, like a transverse polarization, just like this, where you have this one additional.
Is this the phi before this? The phi is assumed as a delta function, right?
Yeah. So in the non-relativistic limit, it is a delta function.
And
in the
now
moment space.
you are considering the correction to the non-relativistic, or you use a relativistic function itself. I mean, this difference, right?
Yeah. So the delta function is the first term in this expansion.
This expansion, I mean.
Yeah, this is in different system of coordinates variables. It looks different, but you can relate this to the other coordinate system, and then the first term would be a delta function.
So the 0, 0, 0 is the.
Yeah, so if you put this to 0, so then you have just the delta function in
It's
terms
all
of
zero.
Z.
One k all 0, 0. You have one delta function, but
Yeah.
But the other one has.
Yeah, but remember that we are now in terms of position variable. If you take the Fourier transform, then it becomes the delta function in momentum space. Yeah. Yeah. Anyway, we get some relativistic correction. There's an additional constant that can be written in terms of these NRQCD matrix elements. So this is basically the leading order NRQCD matrix element, and this is like the average of the quark velocity, essentially. So you can include this also. And then for the numerics, we need an actual model for this dipole amplitude that I talked about. So the way we do this is that we take the initial condition from an NLO fit to structure functions. And in this paper, they actually had plenty of different fits. So we have been using 6 of those fits in our results. So basically, we have 3 different approximations of the NLO PK equation that is used for the evolution of the dipole amplitude. And then we consider 2 different starting points for the PK evolution. So you can have this earlier starting point or this later one. So this like Bjorken x would be 0.01 for this. And for this Bjorken x would be 1.
What kind of? You said there's different amplitude.
Yeah, so they.
That's the 3 times 2. That's where 3 and 2.
Yeah.
Different approximation. We consider 3. Okay.
Yeah, there were actually even more fits in this paper, but we only considered 6. Yeah, so then some results for J-side production as a function of this photon virtuality. So first on the left, we have just the non-relativistic limit. We have the leading order result in black. You cannot really distinguish between different lines here, but there's one leading order result. So this uses some other leading order fitted dipole amplitude. And then we have the NLO results using the 6 different dipole amplitudes. So you have 3 different evolutions. So this is given by the color, and then the 2 different starting points for the evolution. And as you can see, there's not that much difference with leading order next to leading order and these different dipole amplitudes. Of course, this is a logarithmic plot, but still everything seems to agree with the data except for these small values of the Q squared. So here you get some overestimation of the data. But then when you also include these V-squared relativistic corrections at leading order, then these are very important for this small values of Q squared, and then you get a better agreement.
So the LO,
Maybe we were asking the same question. So the relativity correction actually is negative?
Yeah, it's negative. So the reason is because it modifies the.
Actually, it's pretty.
Yeah, it is.
Significant.
It's significant for this small Q
For
squared
no
values. Yeah. So we actually had a previous paper at leading order looking into relativistic effects, and we found that using just the delta function at leading order has the same effect. So, yeah, you need to have some kind of.
What's the reason?
Why it's important, or
Why is it negative?
oh yeah, so I guess it changes the shape of the wave function. So if you take the non-relativistic limit in the coordinate space, it's just like this. But then the corrections, they kind of
I see.
more like this.
Because your dipole amplitude or whatever your hard part also decrease when you have a different shape, right? So
Yeah.
okay, kind of.
Jani, so the LOBK has running of the coupling, right?
Yes. Then you can also look at the same thing as a function of the energy now. So again, now we are looking at this Q squared is basically 0. So on the left, this non-relativistic limit overestimates the data. When we get better agreement. For small values of the dipole, you can see that actually our cross section goes negative, which is not too good. So, but this is for this dipole amplitudes with starting earlier. But we're not entirely sure of the reason, but the thing is that this NLO correction can actually be quite large. So this is the reason. But on the other hand, we are considering the high energy limit, so maybe we shouldn't be too worried about this region, but it's still something to keep in mind.
So the dipole amplitude you use in this calculation is coming from the inclusive DNS fit?
Yes, it is fitted to structure functions.
Okay.
Yeah, at next to leading order.
At next to leading order. I mean, of course, you could do a combined fit with relativity correction or not, right?
Yeah.
I mean, here it looks like your relativistic correction is important.
Yes, it's true. So if you want to do fit, then you have to decide okay, what is your wave function? It's a complication.
I think there is something maybe you don't mind pointing out. It looks like the difference between LO and NLO is not huge, right?
Yes.
I mean, except, okay, there is some regime, but I think this is an artifact of the fact that one is fitting the header data with LO, and there is a parameter which you can tune in the LO, which can slow down the evolution.
So here, leading order means
Yes.
that you use also leading order.
Yes, so there's a different dipole amplitude used for the leading order and next to leading order.
Okay.
So it is true that the agreement with the data could be just because they have been both fitted to the structure function. So if exclusive vector meson production is similar to structural function, and it to some extent it is very similar, so you might expect good agreement.
So it kind of underestimates a bit the importance of the NLO, right?
Yes,
In some sense.
you would say that.
So is that why the PQCD calculation of J-side photo production at NLO, they found huge differences between leading order and NLO, and you find much smaller?
Yes, so I don't exactly know what PDFs they use. how they have been fitted, but it could be one reason. Also, they are considering q squared equals 0 in the non-radius limit. So based on our calculation, we should include some radius corrections also.
I mean, the other thing was they found, I mean, they looked at the relative importance of quarks and gluons in
Yes.
target, and they found, they found cancellations between gluons in leading order and NLO, and so quarks are really important. Yes. You have similar.
Yes. So in a sense, our interaction with target is just gluons, but the way to compare these two approaches is hard, because you could say that their work contribution is included in the dipole amplitude. Like their work contribution comes from gluon exchanges from quarks at NLO. So it might be included in our dipole amplitude, and we don't really have separate quark and gluon contributions like that. So it's a little bit different. Okay, so these are for J psi. For we also consider epsilon. Here we only take the non-relativistic limit because the relativistic corrections are smaller. There's not too much data. This is as a function of energy. We get good agreement with the data, but there's not too much of it. So there's not that much to say. But also here, leading order and next to leading order are not too different.
So when you say total epsilon, epsilon 1s plus 2s plus 3s?
Oh, it's just 1s.
Okay.
Yeah.
So did you also have a relativistic correction?
Yes. Here we kind of plus leading order plus and leading order plus. But they are on top of each other. So.
Yeah, so
Yeah.
That's to justify your correction to your
but-
side, because here it's velocity is very small.
Yeah. To be fair, so you have to take some value for the energy estimate element, which gives us relative corrections, and that matrix element is very small for epsilon. And
Okay.
I don't.
For light vector, for example, rho or phi meson, they vector much larger. Realistic.
Yes, so you can really use NRQC for those. So actually, so I would now turn to light vector meson correction. I'm not sure how much time I can.
can you wrap it up in 10 minutes at most?
10 minutes, I think I can do that. So there's not. So there's some differences between light vector meson correction. So now we are considering the large photon virtuality limit, and then because this photon wave function is a Bessel function that depends on the dipole size and the q, and this goes like e to the minus rq. So if you take q is very large, then this dipole size has to be very small. And based on that, you can think, okay, you have your meson wave function, then you could do like a Taylor expansion for it in terms of the transverse coordinate. And then you will find that, okay, these higher order terms are then suppressed by the photon virtuality. So there's only this dependence on the z. And this is actually given by this distribution amplitude of the meson. So this is like the leading twist distribution amplitude. And then you can say, okay, our leading order wave function, this way is just distribution amplitude times the delta function in momentum space. And also we are considering only longitudinal production because it turns out that it dominates in this large q squared limit. Then we also need to renormalize this meson wave function again, and we do this in this way that you have your bare wave function, and then we write this renormalized wave function in this form. It's bare by plus some term that we call the ms bar scheme. So here this k is like the ERBL kernel, because if you then calculate the dependence on this factorization scale, you can write an evolution equation like this, and this is called the ERBL equation. You have the same kernel here. And what this evolution equation does is basically resums these gluon exchanges up to this factorization scale. And so very briefly, okay, what this ERBL evolution does is that if you take consider the distribution amplitude, it turns out that you can write it in terms of these eigenfunctions of the ERBL evolution, and then only these coefficients evolve in terms of this factorization scale. Now, if you go to very large μf, you find that there's this asymptotic state where this converges. And so you can consider like, okay, if we start from μf is 1 GeV, and we have these two different distribution amplitudes in the solid red and blue lines, and then we evolve it to 50 GeV, then you go from this solid to dashed lines. And this gray line then is the asymptotic limit. So you can see how this evolution brings it towards the asymptotic limit. But it turns out that in our case, actually, we can basically take this asymptotic limit because this second coefficient, that it's like deviations from the asymptotic limit is like 0.1 for rho and phi mesons, and also there's some suppression when we actually calculate it. So basically, you can take our results to be in the asymptotic limit.
Oh, this is for vector meson, right?
Yeah, for light vector mesons. So for rho or phi. Yeah, and then we get some results again, finite. It's a little bit nicer actually than the heavy vector meson case. And then we can do similar plots as before. So here's rho and phi production, and again using the same dipole amplitudes as before as a function of q squared. And also we are calculating on the longitudinal production, but we seem to get a very good agreement with the data. But one caveat is that there's not too much data of just the longitudinal production, so we actually also compare this longitudinal transfers, because in the large q squared limit they should be roughly the same. And actually, if you go to small values of q squared for phi production, you find that very funnily we agree with the total production and not with the longitudinal one. But this is kind of like just coincidence, and you cannot really trust these results in this small q squared region. But for large q squared, this seems to work very well. And we also calculate this in terms of the energy. Now, there's not too many data points. There's some differences between the different dipole amplitudes, but not too many. But again, seem to agree with the data, at least for what there is. Okay, then finally the summary. So exclusive vector meson production is a good probe for saturation effects. And we have considered it at next reading order in two different limits. So for heavy vector mesons, nonrelativistic limit; for light vector mesons, large photon virtuality. In our productions in total are moderate, but there's the caveat that they're probably captured mostly by this dipole amplitude fit. So yeah, when you fit the dipole amplitude to structure functions, then it's not probably surprising that we get a good agreement with the data and the leading order. And in the future, one could also consider nuclear targets. So these were all for protons. For nuclear targets, we'll also need to do some extra modeling for the dipole amplitude. And yeah, one could maybe do some more phenomenology of this, like try different heavy quark masses and such. Okay.
Thanks a lot, Jani, for the great seminar. We have further questions for Jani?
Let's go sort of a follow-up one. I'm still troubled by this issue. What happens with the quarks in the target, where, you know, there's the PQCD finding that they're really important, and yet color glass condensate, they don't really fit in. And can you know, say more where how the quarks come in?
The way I see it is that when they say quark contribution, they have a diagram like.
I think you might be able to draw even in the screen with the pencil.
Yeah.
Okay. What's this one? Yeah. Okay. So you have your photon, and then you have your target. So I think their quark contribution here is like they actually have gluons emitted from this quark, something like this. And if you consider CGC, then we just say, okay, we have some gluons coming from the target. We don't know if they're coming from the quark, coming from the gluon. It's all the same to us. So this is all included in the dipole amplitude. So we are just concerned that, okay, this target is some kind of color source, different color fields. So I think it is, in a sense, included in the dipole amplitude.
Okay.
When you do this next leading order, I mean, part of that actually is absorbed into some kind of evolution.
Yes.
Of that. And then, but normally when you do factorization, there are really corrections, right? It depends on your renormalization scheme. Is that the case here? It's completely be absorbed into the evolution of your
No, you have also some genuine analog corrections.
There's genuine.
Yeah.
I didn't actually ask you what kind of renormalization scheme you use here.
For the whole calculation.
Yeah.
So in the let's see how far away it was.
Because the scheme depends on, I mean, they find the genuine next linear order correction depends on the scheme, right?
Yeah, so there could be some scheme dependence, that's true. So for the plus momenta, you have to regulate this gluons momentum. So we use this cut of alpha. And then basically what you find is that you have this log alpha correction that goes in